In this video, we're talking about electric field superposition. Hopefully you've watched the two previous ones that deal with a couple of charges. I wanted just to wrap up the idea by looking at a very common textbook problem, which is a bunch of charges that are oriented on the corners of a square. So if there's a square here, we've got positive charge here, here, and a negative charge right here. And see, they're all oriented on the corners of a square. And what the question might ask then is, what is the net electric field right there at that point? That's what the question might ask. And so the square might have some dimension d about each side. Let's just see what happens here. So the way you'd approach this problem here, they all have side length of d because it's a square. The way you'd approach this problem then is just to add the electric field at this point because of each charge as if the others don't exist. Here's what I mean by that. Here's a positive charge, and we know electric field lines go outwards away from positive charges in all directions, but one of the electric field lines will actually go right through this point. If this is charge 1, 2, and 3, we can call this the electric field due to charge 1. Now we go down here to charge 2, also a positive charge. Again, electric field lines pointing out in all directions, but one will happen to go right through this point like that. We can call it E2. And lastly, the negative charge, we know electric field lines point towards negative charges. So there'll be an electric field line sort of goes in towards like that. This can point down like that, and we'll call it E3, something like that. So you can see the superposition case that we have in front of us here. Here's the big dot right here. We have three electric field lines going through it, and so the job is to sort of add them together to figure out, well, how they superimpose. And so what we need is to work on it a bit now. Essentially, we have a dot here with three electric fields in it. We want to add them all together to get one total electric field. So the way I'd proceed with this then is to say, okay, well, we have x and y components here. So the E total x is going to be E1x plus E2x plus E3x. So where is this coming from? I'm just saying the x component of the total electric field comes from the sum of all the other x components. So what has an electric x component here? Well, looks like E1 is all in the x direction right here. So we can just replace this E1x with just E1 right there because that's all along the x-axis here. E3 looks like it doesn't have an x component at all. So the E3x, that's just going to be 0. There is no x component. And E2 here is sort of the troublesome one here. Not really troublesome, but it requires a bit of work to figure out in that now we need an angle. We need to do some vector addition here. Here's an angle in here, alpha. That would be the same as this alpha. And because it's a square, alpha is going to be 45 degrees, but we'll go ahead and leave it as alpha for now. And if you look very carefully at E2 here, it has an x component this way and a y component this way. This side here will be E2 times the sine of alpha, and this side right here will be E2 times the cosine of alpha. So we see we have a couple components going on there, and the E2 cosine alpha is the x component, so we can go ahead and add an E2 times the cosine of alpha in there. This will be our total electric field in the x direction. So we'll have a result already. It's a bit incomplete. We'll look at what to fill in for E1 and E2 in just a second. Let's look at the y components now. So E total in the y direction here will be E1y plus E2y plus E3y. So in other words, the total y electric field is none other than the superposition of all the other y components that might be in the problem here. Let's see what we have. What about E1? E1 doesn't have a y component at all. It points all in the x direction, so this is just going to be 0 right here. How about E2y? E2y looks like it's this component right here. That's the E2 times the sine of alpha. That's this upwards pointing component here of this right triangle here. And we look at E3y. E3 is all in the y direction, but it's down, so we'll put a minus sign in front of it. That'll just be a minus E3. So we have our second result here. We have E total in the y direction equal to this quantity right here. And we're almost at our answer now, but what we like to do is a couple things. We'd like to, first of all, put in something for alpha. Now I'm keeping it kind of general here. This is a square, but you might be working on a rectangle or something like that. But it looks like in all this case here, alpha is going to be 45 degrees. That makes it really easy to take the sine of the cosine out. You can just punch in your calculator or whatever ratio you remember from high school, plug in. But what are you going to do now for E1, E2, and E3? What are you going to put in for those? Well, for those, you're just going to fall back on the good old electric field equation to know what to fill in for those. In particular, that electric field is always K times Q over R squared. Shouldn't be a problem at this point. So what you'd fill in now, say, okay, well, what is E1? E1 is the electric field because of point 1. So we have a charge here, which is a distance d from that point right there. So E1 looks like it's to be K times Q1. And of course, Q1 is however much charge is in this. It could be, well, look in your book, hypothetical, theoretical, whatever. But whatever charge is in this positive, that's your Q1. And of course, the distance is d, so we'll just put a d squared here. This is E1. This E1 here, you can plug in anywhere E1 appears, in particular right there. Okay, what is E2? Well, same sort of thing. It'll be a K times Q2. Q2 is the amount of charge in this charge right here. Now the distance between them, of course, is going to be the hypotenuse of this square here, which I believe is going to be something you can get from the Pythagorean theorem. In particular, it'll be the square root of d squared plus d squared. That's the Pythagorean theorem, but of course it's r squared in the bottom, so you have to square. Now I'll let you simplify that. You can see it's going to be a square root of 2d squared, so it looks like the square root of 2 times d. Don't forget to square the whole thing because of the r squared in the electric field equation. But this is going to be your magnitude of E2, which you can put in here and here. Okay? E3 is found the same way. Again, the K times Q3, the amount of charge in Q3 is the amount of charge right there. And the distance this charge is from the point of interest is also d, so it'll just be a d squared in the bottom right here. So with that, I believe the problem is now complete. I'll just sort of draw where you put the results, or those can completely mess up my drawing here, but that's okay, so we're about done. This E1 here that you found, you can put in right there. This E2 that you found, you can put in right there and simplify. And this E2 can also go right there. This E3 that you found is E3 that can go right there. So see, the point is that you can just bring all this stuff together into some couple of big sort of relations there to find the x and y components of the electric field. So there's a bit of algebra to do, which I'm not doing because it would just fill this whole thing and make the video 4 times as long. Let me just keep going a bit. Assuming you've worked on all those results and you sort of have them out, what do? My claim is that you'll have an E total x and an E total y, and each one will be equal to something. You just sort of have them. Maybe you simplify it, or maybe you plug in numbers or whatever. How do you sort of wrap it all up? Well, you do a couple of things. Is one, the magnitude of the total electric field is going to be found from the Pythagorean theorem, as it always is for these vector things here. The E total x squared plus E total y squared. This will be the magnitude. That's the total electric field that exists at this point. And the angle you can get relative to the axis here is always going to be found from the inverse tangent. So you can say that, well, I shouldn't use alpha because that's already in the problem right there, because alpha sort of exists up here. I don't know what the angle of the vector is going to make. Let's just call it something like theta then, or something. The angle the vector will make with a positive x-axis then is going to be the absolute value of E total y over E total x, something like that. And the way you can get that from is sort of you draw a Cartesian coordinate system and say, suppose E total x and E total y were both positive. E total x would sort of be over here like this, and E total y might be sort of up there like that if they're both positive. If one's negative, you have to draw the arrow properly. But now what I've done here is this line right here, E total, is the E total you find from the Pythagorean theorem, and the theta would be this angle in here that you'd find. So it would be the angle relative to the y-axis, x-axis, where theta, the tangent of theta is opposite of hypotenuse. So that's where the inverse tangent comes from. But hopefully the inverse tangent is something that you know from your previous study of how vectors work from mechanics and so on. So anyway, so once you get all the algebra done, by finding your components, you can bring them all together into one final vector and one final angle to complete your problem.